All right, moving on to section 3.2, we're talking about higher order equations. That means things that have a higher degree than 2, right? So we've talked about linear equations. We've talked about quadratic equations. The things that we're talking about today are going to have a higher degree. They might have a higher power, the highest power of 3, 4, 5, just whatever we see. These things are called polynomials that we're looking at today specifically. We're looking at polynomials. This is the standard form of a polynomial, but don't let this scare you. The standard form is just saying that essentially we have a bunch of coefficients and a bunch of x's with exponents. And in standard form, those exponents are in descending order, right? They go from highest to lowest, all the way down to just a constant term that does not have an x at all. The highest exponent of the polynomial is called the degree. So for example, this is a polynomial, v of x. It has a degree of 3 because the highest exponent is 3. It's important to note that degree and coefficient are two different things, right? The coefficient here is a positive 4. The degree is a 3. One thing you'll note about polynomials is that this thing is smooth and it's continuous. It doesn't have any sharp peaks and it doesn't have any holes or gaps. And we'll talk about that a little bit more here in a minute as well. But all polynomials have those characteristics. So ones that we've already talked about linear equations, right? Here are some examples of linear equations, and here's what a linear equation looks like graphed. Here are some more linear equations, and here's what they look like graphed. We've talked about quadratic equations. Here's what quadratic equations look like graphed. Notice that all those are also smooth, and they're also continuous. We're looking today at higher degree polynomials, right? So third degree, such as cubics, those are called cubics. Fourth degree are called quartics. And anything higher than that, we just call it nth degree. So if we had one that was a degree of 6, we just say it's a 6th degree polynomial. The domain of any polynomial function is all real numbers. That's what's saying that it's continuous, right? The domain is all real numbers. It goes as far left as you want, as far right as you want. It never stops. It never has a break. So for example, this is not a polynomial because it has a break, right? This is not a polynomial because it has a break in that graph. They're also smooth, and so this is not a polynomial because it has a sharp point. Absolute value is not a polynomial because it has a sharp point. Just looking at this graph right here, this is a polynomial because it's both smooth and continuous. That's one way when you're looking at the graph to tell if something's probably a polynomial or not. Here, a little bit of housekeeping. I don't know how much this is actually going to show up on your ALEX, but when you're talking about limits, when you're talking about end behavior, I'm going to give you a better idea of how to find end behavior, but we talk about as this notation right here is as x approaches infinity. And we're going to talk about as x approaches infinity, what does y do? Does y also approach infinity? Does y approach negative infinity? As x approaches negative infinity, does y approach infinity or does y approach negative infinity? That end behavior, we're talking about, let's say I graph this polynomial, right? Smooth and continuous. I could say something like as x approaches negative infinity. That's the left side over here, right? X is approaching negative 3, negative 5, negative 7, negative 100, negative 1,000. X is approaching negative infinity. And what is y doing? Y is going down. Y is approaching negative infinity, right? So as x approaches negative infinity, y, f of x, also approaches negative infinity. As x approaches positive infinity, that'd be 1, 2, 5, 100, 1,000, all the way over to the right. As x approaches positive infinity, y, or f of x, also approaches positive infinity in this graph that I drew. A lot of times we'll just say that they're trending upwards or they're trending downwards. So I would say on this one, the right side is trending upwards, the left side is trending downwards. There's some ways to figure that out based on an equation. And really, your leading coefficient is going to tell you a lot, and your degree is going to tell you a lot about that. here are the rules. You can look at this chart for a second. Pause the video and look at this chart. We're going to really look at the right side first, and then that's going to help us determine the left side. So for the right side, if the leading coefficient is positive, then the right side is going to go up. If the leading coefficient is negative, the right side is going to go down. For the left side, if the degree is even, then the left side is going to do the same exact thing as the right. So if the right was going up, then the left will be going up. If the right was going down, the left will be going down. For the left side, if the degree is odd, then the left side is going to do the opposite of what the right was doing. So let's look at these two examples that we have here. We'll first look at the right side. So the leading coefficient. Here, the leading coefficient is negative. That means the right side is going to be going down. The degree is odd. That means that the left side is going to be doing the opposite of the right side, means it's going to go up. And we could do what we don't know what it does in the middle. We just know that far left it goes up and far right it goes down. We could write this in the same notation that we had earlier. So as x approaches positive infinity, that means we're going to the right, y, or f of x, approaches negative infinity. The right side is going down. That's all this is saying, is the right side is going down. Right side. The left, as x approaches negative infinity, that means we're headed to the left. F of x, or y, is going up, so it's approaching positive infinity. See if you can figure out that next one. Looking at it, the leading coefficient is negative, so the right side is going down. The highest degree is even, so the left side is doing the same thing, which means it's also going down. So if I was to describe the right side as x approaches infinity, going to the right, then y, or f of x, is going down, approaching negative infinity. The left side I can describe very similarly as x approaches negative infinity. That means we're going left. Y, or f of x, is going to be going down as well, negative infinity. This is the left, this is the right. I'm just going to use my arrows here to describe these. I would again pause the video, see if you can figure all these out, and I'm going to write the answers here in just a second. Since the leading coefficient is negative, the right side is going down. Since the highest exponent is even, the left will do the same, it will also go down. Since the leading coefficient is negative, the right side will go down. Leading coefficient is even, the degree is even, so the left side will also go down. Here, leading coefficient is positive, the right side will go up. Exponent is odd, and so the left side will do the opposite, and it will go down. We can just describe this one with that limit notation. So as x approaches positive infinity, that's the right side, y, or f of x, is going upwards to infinity. The left side, as x approaches negative infinity, that's going leftwards. Y, or f of x, is going to also approach negative infinity. It's going downwards. So this is describing this piece. This is describing this piece. In any equation, in any polynomial equation, the degree is going to tell you how many solutions you hope to get, right? So here the degree is 3, the highest exponent is 3. We're really hoping to get 3 solutions here. We really want to get 3 solutions. To find those solutions, to find the zeros, 0, x-intercept, root, here we can make a list of those. We have 0, we have solution, we have x-intercept, we have root. Those all in math, aside from solution, can mean different things, but all these mean the same thing. They mean that where is y 0, right? If we're looking for an x-intercept, where is y 0? And so to solve these types of equations, where it asks to find the zeros, we're just going to set the whole thing equal to 0. 0 equals, I shouldn't have put that parentheses there, x to the third plus x squared minus 9x minus 9. The way that you want to solve a polynomial, if you can, the same way as quadratics, if you can solve by factoring, then absolutely do that. It's going to save you a lot of time and stress. So what I'm going to do is solve this. It's got 4 terms. You can go back to the review on factoring, right? And remember that to factor something with 4 terms, we're factoring by grouping. And now I can group my outside with my outside, my inside with my inside. And now I can factor the first thing as a difference of squares. That's x plus 1. I wrote x plus 9 here. That's x plus 1. I'm sorry. That was my mistake. And so our x-intercepts, our roots, our zeros are positive 3, negative 3, and negative 1. Remember, we're just looking for the things that would make that 0. Really, when we go to graph that, those are x-intercepts, so that's the points 3, 0, negative 3, 0, negative 1, 0. Pause the video and see if you could find all of the zeros of this next function. To find them, we'll set the whole thing equal to 0. Start factoring by grouping. Finish factoring by grouping. That first term looks like a difference of squares. Factor it by difference of squares. Set the whole thing equal to 0. And those are our x-intercepts. Those are our solutions, our roots. All right, one more here. Find the zeros. We know if we're finding the zeros, we need to set the whole thing equal to 0. Whenever I'm factoring, I'm seeing, oh wait, that's an x to the third, okay? So I'm seeing that there is a GCF. We can take an x out of all these. And since the leading term is negative, I'm just going to take a negative x out of all of them. And then what I'm going to do is, this is 3 terms, so I'm going to use star method. And that's a negative 8, so to make negative 8, we need negative 4 and negative 4. Multiply to 16 and add to negative 8. Again, if you need to, go back and review that factoring unit. And so my solutions here are 0, 4, 4. And this brings up a new point here. We said initially that we want as many solutions as we have a degree, and we got 3 solutions. Even though one of them repeats, whenever you type in your unique solutions, our unique solutions are 0 and 4, right? We still got 3 solutions, though. Note 1, 2, 3 solutions, right? What we say here is that since the 4 is repeated twice, it has a multiplicity of 2. That's multiplicity is how many times something is repeated. That word is listed down here. The multiplicity is how many times something's repeated. So 4 has a multiplicity of 2. We still have 3 solutions. I have a 0 and 2 4s. That's going to mean something special for our graph. When a root has a multiplicity that's even, that's going to mean something special when we get ready to graph these things. Try to find the zeros of the next one. Same start. We can factor an x out of everything. Use star method. Set it equal to 0. Notice that we have 0 and 2 negative 5s, right? Negative 5 twice. So negative 5 has a multiplicity of 2. We still have 3 solutions, just that negative 5 is repeated twice. Okay, here's the point that I was going to make, is that if it has an odd multiplicity, that means if it shows up 1 time or 3 times, so this only has a multiplicity of 1, right? It only shows up once. If it has an odd multiplicity, when you go to graph it, it's going to pass straight through that point. So here, for example, it passes straight through that point. It has obviously an odd multiplicity. Here, if it touches and turns around, that means it has an even multiplicity. So this, for example, we have 0. That only showed up once. We have 4. If we were to write this out, that'd be x minus 4, right? X minus 4 squared. 4 has a multiplicity of 2, and so at that point 4, it does not pass through. It turns around. 4 has a multiplicity of 2. An even multiplicity, it's going to turn around. Not an even solution, but an even multiplicity. Notice 0 had an odd multiplicity, so it passed straight through. All right, this one's already factored for us. And so on that first one, we know we have a solution of 4 with a multiplicity of 2. We know we have a solution of, if I set this equal to 0, 2x plus 5 equals 0. 2x equals negative 5. X equals negative 5 over 2 has a multiplicity of 3. And so I have 5 solutions, right? I have 2 4s and I have 3 negative 5 over 2s. For this point right here, it's going to pass through. because the multiplicity is odd. For this point here, it's going to touch and turn. It's going to turn around because the multiplicity was even. For part B, if we were trying to find the zeros, what we would do is we would take out a GCF, so 0 equals x squared minus 2, and then I could say that would be 0, right, with a multiplicity of 2. For this one, x squared minus 2 equals 0, x squared equals 2. Take the square root on both sides, and x equals plus or minus square root 2. Don't forget, if you take the square root on both sides, you do get a plus or minus. And so since we wanted 4 solutions here, we got 2 and 2. Makes a total of 4 solutions, right? The positive and negative square root of 2, each of those only have a multiplicity of 1, right? That's the positive square root of 2, the negative square root of 2. Each of those shows up once, 0 shows up twice. Same exact types of problems. Take a second and see if you can solve these. So here, negative 3 would make this blank 0, and it shows up 4 times. Here, positive 1/5 would make this blank 0, and it shows up 5 times. On the bottom one, you want 6 total solutions. Set it equal to 0. Factor out the GCF. Notice that 0 shows up 4 times. And then the same way solving this, positive or negative 7, that's the same thing as square root of 7, negative square root 7, positive or negative square root 7. So we have 6 total solutions. We have 1, 2, and then 4 there makes 6. 4 zeros. All right, the intermediate value theorem, what it's saying is we can sort of figure out where a solution is. If we don't know exactly where a solution is, we can know that a solution is inside of a range if we just check some points. If one of those points is below the axis, right? So if this point is below the x-axis and this point is above the x-axis, it must have crossed through that x-axis at some point. So there's at least one solution in between those, right? Here, let's just look at an example here. It's going to help. Show that this has a 0 on the interval 1 to 2. So what we're going to do is we're going to take first, what's f of 1? I'm just looking at the numbers in that interval. And then I'm going to say, what's f of 2? And if one of them's positive and one of them is negative, that means that it passed through the axis between 1 and 2. All right, f of 1 would be 1 to the 4th plus 6 times 1 to the 3rd minus 26 times 1 plus 15. Type that in your calculator. This would be 2 to the 4th plus 6 times 2 to the 3rd minus 26 times 2 plus 15. Type that one in your calculator as well. I'm going to type it in my calculator while we're sitting here. 1 plus 6 minus 26 plus 15. So this one turns out to be negative 4. 2 to the 4 plus 6 times 2 to the 3 minus 26 times 2 to the 1 plus 15. For me, turned out to be 27. Notice that this one is a negative number. This one is a positive number. So if I have the point 1, negative 4, and the point 2, 27, that means that there is a solution somewhere between those, right? It has to cross through the x-axis to get from one point to another. It doesn't tell us what that point is. It just tells us that there is a solution somewhere between 1 and 2. That's all it tells us. All right, same thing here. Show that this function has a solution on this interval. So what we're going to do is first check the first number, check the second number, we'll evaluate. Notice that I just typed it straight into the original function. The same thing with negative 3. One of them turned out to be a negative, one turned out to be a positive. We can use the same logic. As long as they have different signs, there must be a solution somewhere between negative 4 and negative 3. So negative 4, negative 9, negative 3, positive 12. It must have passed through the axis to get there, right? So somewhere on this interval, there is a solution. All right, putting it all together, when we go to graph these things, what we're going to do is first look at the end behavior, right? We're going to determine whether it's going up or down or left or right. We're going to determine the end behavior on the right, the end behavior on the left. That's going to give us a general idea of what the function is doing at the extremes. Then we're going to find the y-intercept. That means we're going to plug in a 0 for x. Then we're going to find the x-intercepts. So we'll find the y-intercepts. We'll find the x-intercepts. And then we're going to graph that. We're going to plot those and graph it. If we need extra points, then we can go through and just plug in numbers to find extra points. Most of the times we'll just go based on what we have, okay? And then we're going to draw a sketch based on those things. Remember that the curve is going to cross the axis if we have odd multiplicities, and it's going to touch and turn around if we have even multiplicities. The rest of this, if we need to, if we wanted greater accuracy, we could do these things. So we could plug in more points. We could plug in more points and make our graph just even more accurate. We could also do an odd and even test, which we're just not going to do in this class. Let's try to graph this thing, just based on exactly what we just said. First, we'll find the end behavior. So since the leading coefficient is positive, here I'm just going to go on to draw my graph, okay? Leading coefficient is positive, the right side's going up. Exponent's odd, the left side's going down. I'm just getting a general idea. I don't know right now what happens in the middle, right? But I know that on the right it goes up, and I know that on the left it goes down. Now let's find the y-intercept. Y-intercept. That means we could plug in a 0 for x. Y equals 0 to the third minus 9 times 0 equals 0. So that's the point 0, 0 is our y-intercept. We can color code these things. All right, find our x-intercepts. So our x-intercepts, we sub a 0 in for y. This is true for all math. If you want to find the y-intercept, you plug a 0 in for x. To find an x-intercept, you plug a 0 in for y. I can factor a GCF of x out. And then this is a difference of squares. And so my solutions here are 0, 3, -3. I can graph those. Here, let's pick a different color here. 1, 2, 3, -1, 2, 3, and 0 is the point that we already have there. Notice that all these had a multiplicity of 1, multiplicity of 1, multiplicity of 1, multiplicity of 1. That means it's going to pass through every single one of those. It's not going to touch and turn around. It's going to pass through every one. So what I need is for it to go down on the left. Okay, I've already got that. Pass through that point, pass through that point, pass through that point, and go up on the right. I can erase my extra little arrow here. That's my sketch of my graph. This is f of x. That's my graph of f of x. That's really all we need. Take a second to try this one. Find the end behavior, find the x and y intercepts. Pause your video because I'm about to show the answers. Here's your end behavior. Here's your x-intercepts, your y-intercept, and here's what your graph looks like. Again, all of these had an odd multiplicity, so it just passed straight through every single one of them. Same thing here. Take a minute, pause your video, see if you can solve it. This is the last one. Here's your end behavior. The degree is 4 here. It's sort of, this one's a little bit harder to see, but notice that we have sort of 2 x's there, an x there, and an x there. Makes a total of 4, right? The leading coefficient is still -1. If we went through and distributed that whole thing, which you could do, it's just a lot of work, but you know that when you multiply x times x times x, and there's an extra x here, you're going to have x to the 4th, right? And you know that when you multiply them times -0.1, you're going to have -0.1 x to the 4th. So here's our end behavior. Here's your y-intercept, your x-intercept. Oh, we have a multiplicity here. So it's going to pass through at 1, pass through at -2, but at +4, it's going to touch and turn around because that has a multiplicity of 2, which is even. And here's what our graph looks like. We can color code these things again if you'd like. The y-intercept is here. The x-intercepts are here. And since this one had a multiplicity of 2, it had to touch and turn around there. It could not pass straight through. That's the end of lesson 3.2. We're going to keep on chugging with polynomials throughout this unit and see some rational functions as well.